Hello students, today we're going to talk about slope as a rate of change. So today we're going to define slope as a rate of change using real world problems. Okay, so by the end of this lesson you're going to be able to read a real world problem and find the rate of change. Okay, that's what I want you to be able to do at the end of this lesson. Okay, now this is going to be kind of a sit and get lesson. Okay, so what I want you to do is watch the video and take notes on it, but there's not going to be an assignment afterwards. Okay, but you are going to have some problems like this on your test on Friday, so just kind of be prepared for that. So we're still following the same standard, which is write an equation in the form of y equals mx plus b to model a linear relationship between two quantities using verbal, numerical, tabular, and graphical representations. Now we know, because we talked about this yesterday, that slope can be found three different ways. It can be found from a graph, it can be found from a chart, and it can be found from a formula. And we're going to apply that by using rate of change. So from a graph, we know we can do rise over run, okay, which is up and over, okay, up and over, okay, is how we do that. The rise over run. If it is a rise, we know it's a positive slope. If it's a fall, we know it's going to be a negative slope. We know from a T-chart, we know that as of yesterday, we talked about this little triangle, and this triangle stands for delta, and the delta means the change in. Okay, so we've got the change in y, which we know is going to be the pattern on the right side of the T-chart, divided by the change in x, which is the pattern on the left-hand side. And then yesterday, what we looked at is finding slope from a formula, and this was the formula that we used, y2 minus y1 divided by x2 minus x1. So let's see if we can do a couple problems using these formats. So here are two questions that I would like for you to do for your warm-up. In the first one, I would like for you to find the slope and the y-intercept using this T-chart. And I want you to write the equation in the form of y equals mx plus b. In the second question, it says find the equation of the line that passes through these points, 4, -8 and 6, 2. For this particular problem, you're going to have to use the formula that we used yesterday. So pause the video and answer these two questions. Okay, so let's find out how you did. Okay, so in this first one, you're given a T-chart and you're asked to find the slope and y-intercept. Now, what I've always asked for you to do is find the y-intercept first, if at all possible. Okay, so that means that we look for the y value when x is 0. Okay, so here is our y value when x is 0. So our y-intercept is going to be 11. Okay, so in the format that we're going to write it is y is equal to blank x plus blank. This 11 is going to go in the y-intercept spot. Now to find slope, we know that that is our pattern. Our delta y, which is 5 to 8, which is 3. So it's increasing by 3, divided by delta x. -2 to -1 is 1. So our slope is m is equal to 3 divided by 1, which is just 3. So the equation of the line that would make this T-chart is y is equal to 3x plus 11. Okay? So now let's see if we can do this other one. Now in this other problem that I have to use this formula. Okay, so like I told you yesterday, what you're going to do is you're going to identify the points. So I'm going to say that this point is number 1, this point is number 2. So what that means is that this is x1 and y1. This number right here, the 6 is x2 and the 2 is y2. So now that I've got them identified, I can plug them into my formula. So I've got m is equal to, well, y2 is 2 minus y1 is -8 divided by, and then we do x2, which is 6, minus x1, which is 4. And then we do our math. Okay, so I'm going to do this without using the calculator. So 2 minus -8, I know I'm going to change my signs. So I change subtraction to addition. Next to its opposite, I end up with 2 plus 8, which is 10, divided by, and then 6 minus 4 is 2. So 10 divided by 2 is 5. So the slope in this problem is 5. And that's really all I wanted you to do in this second question. First question, we could find everything. In the second question, we can just find the slope right now. Now, there is a way to put this into this equation, y equals mx plus b. We're just not going to do that just right now. Okay, so now what we're going to do for the remainder of this lesson is I'm going to talk about some scenarios. And what I want you to do is see how slope is nothing but a rate of change. And we can use that rate of change to make predictions. Okay, so here is our first problem that we're going to look at. Okay, it says the following represents the graph for a helium balloon's flight. Now, you've all seen helium balloons and how they fly, and they go straight up in the air because of the helium, because it's lighter than air, so it floats. Okay, so this one right here says, okay, in this graph, every time you look at a graph, I want you to look at a couple things. First off, look at the axis labels, the axis labels. So our x-axis is labeled time, and the time is in minutes. So each one of these is referring to minutes. 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, and so on. Okay? Now, going up the left-hand side, the y-axis is our height in thousands of feet. Okay, so that's what we're looking for. So it's 1,000, 2,000, and so on and so forth. So if you look at our graph, it says that our helium balloon started where? What elevation did it start at? What height did it start at? It started at 0 feet at 0 time. So we release the balloon, and then what does it do? Okay, our balloon gradually goes up and up and up, and it's kind of consistent. Okay, so the first question that I'm going to ask you is, what is our rate of change? In other words, how fast is it moving? And that's what the rate of change would be in this particular problem, is how fast is it moving? Okay, so in order to do that, we find slope. Now, slope from a graph, we know that we're going to do rise over run. So I told you yesterday, you pick good points. So the first good point we have is this one right here, which is 0, 0. The next good point is this one right here. Well, the next one would be this one, and so on and so forth. So all of those are good points because they cross in the crosshairs. And that's what we identified yesterday, or talked about yesterday, as being a good point. And all you have to do is rise over run. So for this one right here, our slope is m equals, well, what did it rise? What did it do? It rose 1,000 feet with a time of 1 minute. So our slope then is 1,000 over 1, which is just 1,000. Okay, and that's 1,000. And the way we would write this would be feet per minute. Okay, and that's how we would do our slope. So what does that really mean? So if I were to write that in that frame of mind right there, 1,000 feet per minute, that means for every 1,000 feet, it's going to take 1 minute to get there. Okay, so 1,000 feet is 1 minute. So in 2 minutes, it's going to be 2,000 feet. 3 minutes, it's going to be 3,000 feet, and so on and so forth. So when's it going to be at 5,000 feet? Okay, well, from this graph, we can come up here to 5,000 feet. We can go across, and it's going to take how long to get there? It's going to take 5 minutes. Now, we can also use this information as a predictive value, okay, or being able to make predictions. So since this does have a linear relationship and there's a consistent pattern, I can then ask you this question. How long would it take for the balloon to get to 10,000 feet? Well, if for 5,000 feet it took 5 minutes, if the pattern continues, how long do you think it would take for 10,000 feet? Very good, 10 minutes. Okay, so you can use that rate of change as a way to predict future outcomes, because 10,000 feet is not on my graph, okay? But we know it would eventually get there, okay? So let's look at another example. So in this example, it says the following represents the balance in Brady's savings account. Okay, so many of you have savings accounts. You know, it's a place where you put money to save and you want to continue to make it grow, so you add money to it. Sometimes you can get what we call an interest-bearing account, which then would also be putting interest in there, not just the money that you deposit. Okay, so we look at our axis again. Okay, our x-axis is months. So we've got 1 month, 2 months, 3 months, 4 months, and so on. Okay, and we've got on the y-axis, we've got the number of, or the amount of money in the account. Okay, so 300, 400, 500, 600, and so on and so forth. Okay, so that's kind of what we understand. And it looks like there's a steady climb of our graph. It just continues to go straight up. So it makes a linear pattern. Okay, so let's ask some questions. So what's the slope of the graph? Well, again, remember, slope, you find two good points, and you do rise over run. Okay, so let's try this point right here, and let's try this point right here. Those are both two good points. Okay, so based on that, what is our rise over run? So M equals, well, it rises between those 2 points, 200, and it runs 1, 2, 3, it runs 2. Okay, now we simplify that. So 200 divided by 2 gives me 100 over 1, which is just 100. Okay, so that's my slope. So what does the slope represent as a rate of change? So what does that mean? What does that 100 right there mean? Okay, that means, and if we look at it in terms of this one, the 100 over 1, that means that we deposit $100 per, and that's what that little line right there means, per month. So every month we're putting $100 in there. And that's what that represents. Okay, so that's kind of how you interpret this graph. Now this next question is going to be kind of interesting. So what about this? So how much did Brady deposit when he opened his account? So in other words, at the very beginning of his account, how much money did he put in there? Well, if you look at where the graph started, at 0 months, how much money did he put in there? $300. So in this graph, it also tells us that we started with $300. Okay, so that was our beginning amount. And what would we call this value right here? Okay, it's the place where the graph crosses the y-axis. So this would be called the y-intercept. Okay, so this 300 is our y-intercept. And if we look at on the previous screen, we found out what the slope was, that it was $100 per month. So with that in mind, what do you think the equation of the line would be that represents this particular scenario? Well, we know that our graph is going to be y, or our equation is going to be y is equal to blank x plus blank, where this first blank is our slope. Now, what did we say our slope was? Our slope was 100, so I could put the 100 here. And our y-intercept was 300, so we could put the 300 right here. So this is the equation that would make this line. And that's what we're talking about by slope as a rate of change, okay? Dealing with a scenario, and that's what we want to be able to understand. Okay, so let's look at a couple more real quick, and then we'll end the lesson. Okay, so rate of change can also be called a unit rate. Okay, it's very important to understand that. And a unit rate is a comparison to 1. How much for 1? Okay, so when we looked at a couple of these other problems, let's see, like this one right here, what did we compare this 100 to? To 1. How much for 1? Okay, when we looked at this other previous example, how much for 1,000 feet per minute? Okay, and so that's what we're kind of talking about when we're dealing with a rate of change as being a unit rate. Okay, so in this particular problem, it says the average adult breathes in about 37 liters of air every 5 minutes. Okay, so what could we do with that? Okay, well, 37 liters every 5 minutes, I could actually, believe it or not, create a T-chart with that kind of information. So let's see if I can create a T-chart here. So here's kind of the beginning one, okay, where we've got, M standing for minutes, okay, and L standing for liters of air. So for 5 minutes, 37 liters of air. So what would it be for 10 minutes? Okay, well, if 5 minutes is 37, 10 is double that. So we would double the 37 to get 74. Well, what if we had 15? Well, if we would add 37 more, and we'd end up with 111. What if we had 20? Okay, well, we'd add another 37 because it's 37 over 5. Okay, and we'd end up with 148. And we could actually graph that. Okay, where if I were to come over here and look at my graph here, we've got minutes. Okay, and if I used them every 5 minutes, I'm going to just kind of do every 2 lines. So 5 minutes, 10 minutes, 15 minutes, 20 minutes. Okay, and going up the left-hand side, this is going to be liters of air. Okay, and I'm all kind of, since these are kind of weird numbers, I'm going to just do every 20. Okay, so I'm going to do 20, 40, 60, 80, 100, 120, 140, and 160. Sorry about those little pop-ups there that keep popping in. Just don't worry about those. Okay, so I could actually now graph this. At 5, it's 37, so I'd put a little dot about where 37 would be. 10 would be 74, which would be about right there. Okay, and 15 would be about 111, so that's going to be about right there. Okay, and 20 would be at 148, which would be at about right there. And you can kind of see that that kind of does make a straight line, just like that. Okay, so what we want to try to figure out is what would the y-intercept be? So based on our information here, what could be our slope? Okay, so we know that this right here is 37, and we know that this right here is 5. So our slope is 37 over 5, but what I want to know is how many liters of air would I have for only 1 minute? Okay, so what we would end up doing then is we would do a division problem. 37 divided by 5 would give us how much for 1. And if we do 37 divided by 5, you end up with 7.4 liters of air for every 1 minute. So that means that when this graph comes down, it's going to cross the y-axis about right there, which is going to be at about 7.4, okay, per that. Well, actually, it's going to be right here at the 1. It's going to be about 7.4, about right there. And then what would we assume that if we had there at 0, what do you assume is going to be our liters per air at 0? What do you think that would be? At 0, it would be 0. It would actually be 0, 0. Because if you have 0 minutes, you just have 0 oxygen. Okay? So let's take a look at another one. Okay? A teenager's heart pumps an average of 7,200 liters of blood every 24 hours. So what is this rate of change in volume of blood? So again, what we're looking for in this particular problem is how much for 1 is what I really want to know. Okay, so if we had the 7,200 for 24 hours, I want to know how much blood would that be for 1 hour. So again, we take our calculator and we do 7,200 divided by 24. And if you do that, you find out that how much for 1? You end up with 300 liters of blood per 1 hour. Okay, now once you have that, you could do the same thing, and you could create a graph that would represent that information. Okay, let's try one more real fast, and then we're going to sum this up. Okay, so here we go. It says, if it costs $25 to rent a car and 10 cents per kilometer to drive the car, create a graph to find the scenario. Well, the first thing we need to do if we want to create a graph is we've got to create some data. We got to get some data. We got to create like a T-chart, okay? So what I have underneath this little thing right here, this little tab, is I do have a T-chart already kind of created. Okay, so let's see. So to find the rate of change, we've got 0 distance. What would it cost for you to rent this car if you're not going to drive it? Okay, it costs $25 to rent the car, okay, up front before you drive it at all. Okay, so after 10 miles, how much would it cost in order to drive that car? Okay, well, the $25 was our rental fee. And if I drove the car 10 kilometers, how much would that cost me? Well, if it's 10 cents per kilometer, and I'm going to drive it 10 kilometers, 10 times 10 cents is going to be $1. Okay, that's going to be $1. Okay, so if we already paid $25 to drive it 10 kilometers, how much is that going to cost? Well, that would cost the $25 originally, plus the $1 it would cost for the 10 kilometers, which would give me 26. Well, what if I wanted to drive it 20 kilometers? Well, if 10 kilometers cost you $1, how much is 20 kilometers going to cost? It's going to be $2. So that would be 27. What about 30? 28. What about 40? 29. What about 50? 30. Very good. Okay, now once we have our data, we can now graph that. Okay, so what we need to do is set up our axis. Okay, so this is going to be distance. That's going to be my x. Okay, and so this is going to be 0. And I'm going to do every 2 lines. So this is going to be 10, 20, 30, 40, 50. Okay, and then I'm going to do a graph break here. Okay, so I'm going to do a little graph break here. And then I'm going to start here at 25. And then each line is going to be 1. And sometimes when you start the data kind of high, sometimes you'll do a graph break like that in order to facilitate it. So at 0, we know that we're going to have a $25 charge. After 10 miles, it's going to be $26 because our y-axis is going to be money. Okay, 20 is going to be 27, 30 is going to be 28, 40 is going to be 29, 50 is going to be 30. Now with that, we can then make predictions. Okay, so I could, because that graph keeps going at that same steady rate, so I could figure out what if it was 100 miles, or 100 kilometers, sorry, or what if it was 1,000 kilometers. You could then determine how much it's going to cost. Okay, so that's what we're talking about. So let's answer a few questions about this graph. So what does the rate of change represent? The rate of change, when we go back and look at this graph, represents what? What is my slope, in other words? My slope is $1 for every what? For every 10 kilometers. So $1 for every 10 kilometers. That's my slope, right? So that's what that means. Okay, so what is the value on the y-axis? Okay, so our y-axis, what did we put? We put the dollar amount, okay, because that is dependent upon how many kilometers I travel. Okay, then how does it relate to the scenario? Okay, well, the scenario is we're trying to drive a car. We're trying to rent a car to be able to do this. So this right here, the scenario is figuring out how much money we're going to cost. How much is it going to cost us in order to rent this vehicle? Well, we have a $25 fee right at the beginning, okay, before I drive it at all. And then as I drive it, the rental cost increases, okay? And then last question, if you paid the same fee to rent the car, $25, but you had to pay more per kilometer, how would that change the graph? What would that do? If I had to pay more, what would it do? Well, hopefully you realize that if I'm paying more per kilometer, it's going to increase my graph and make it go up higher and faster. Because if I'm paying more per kilometer, then my price is going to increase. Okay, so that's what we're talking about with all of this stuff. Okay, so let's kind of review and finish this up. Let's wrap this up. Okay, so we know that we've got slope where we can find it several different ways. We can find it from a graph using rise over run, up and over, or down and over, whichever the case may be. If it's up and over, we're going to have a positive slope. If it's down and over, we're going to have a negative slope. We can find slope from a t-chart by doing the delta y, or the change on the y side. Okay, so if I look at a t-chart, the change on the y side divided by the change on the x side. And we know that we can find it from a formula. And we can use slope as what we call a rate of change in a scenario. And that's what we're basically trying to learn today. Okay, so I hope that you took some notes on this, because you will see some questions like this on your test review on Thursday, as well as on your test on Friday. And what we're basically looking at is looking at its slope, okay, from a graph standpoint. Okay, typically it's going to be from a graph, and we're going to be using the rise over run in order to find our slope. And then we know that our y-intercept is always going to be the point at which that graph will cross the y-axis. Okay, so until tomorrow, I'll see you later.